Uh, my name is Georgios Keramidas. I'm one of the program chairs of FPL 2020. Welcome to the fifth and the last day of FPL conference. I hope you enjoy the conference so far. We still have one full day. Starting by the third keynote of FPL, which will be given by Michaela Blood from Xilinx. After that, we are going to have the first industrial session with two presentations, one from Cadence and one from Acceler. And after that, we have a session from the main conference in which we have two parallel sessions, one on accelerated machine learning and the second one in synthesis technology and others. After that, there is the virtual exhibition, and just after that, at 6:30 Central European Time, we have the second session on industrial talks. And in this session, we are going to have a talk by Jose Alvarez from Intel. At 7:30 Central European Time, we are going to have two parallel sessions, one on tooled methods for machine learning accelerators, and the second one on research projects. And a 8:15, we are going to have the closing ceremony, in which we are going to announce the best paper awards and also to announce the FPL, the FPL 2022. So I would like to welcome Michaela Blond from Xilinx. A few words about Michaela. Michaela is a fellow at Xilinx Research in Dublin, where she leads a team on international scientists driving exciting research into new application domains for Xilinx devices such as machine learning. Michaela earned a PhD from the Trinity University College in Dublin and a master's degree from the University of Karlsruhe in Germany. And she brings over 25 years of experience in leading edge computer architecture and advanced FPGA and board design in various research institutes and development organizations. She is highly active in the research community as industrial advisor to many EU projects. She serves on the technical program committees of various conferences, and most recently, Michaela received the Women in Technology Award. So, Michaela, thank you for accepting our invitation. The floor is yours.
Okay, hello everyone, and thanks so much for inviting me. It's a really great pleasure to be here today. I hope you're all keeping well. Such a shame we can't do this in person, but 2022, it'll happen. So I'll be talking to you today about innovative FPGA approaches to AI. It's a subject I've been personally working on now for a number of years. I'll definitely talk about FIN, which is our flagship project in this space. Some of you might have heard about it already, but I also have some new material included. Before we go to this, I'd like to start just with 1 minute background in case you don't know who we are. So let's see whether that slide advances. Okay. Okay, so Xilinx Research Dublin was established over 15 years ago. Roughly speaking, there are 7 full-time researchers of us, plus university program. And I'm just representing here the work of these amazing researchers, including Nicholas Fraser, Ken O'Brien, Alessandro Pappalardo, Lucian Petrica, Yaman Umoboglu, and Kees Wissers. They all deserve to be named by name. So our main charter is quantifying the value proposition of our devices in machine learning, whereby we're really hands-on in the approach. So we're building real systems, we're exploring different architectures that we create on the FPGAs, we're optimizing on the algorithm levels. So we're doing a lot on the machine learning algorithms themselves, and we're doing a good bit of benchmarking too to keep ourselves honest. So, and finally, it's worth saying we're operating not in isolation, but really in close collaboration, of course, internally to Xilinx, the engineering and marketing organizations, but also externally. So we work a lot with universities. For example, just to name a few, ETH Zurich, Delft, Heidelberg, Politecnico di Milano, Paderborn, and Darmstadt. And with customers, we are collaborating too. So for example, we've worked with Daimler on the quantization of the neural networks for their gesture recognition in their V-class model, which was pretty cool. So I also want to take the opportunity to shamelessly advertise here our internship program. So typically we have between 4 and 6 interns with us at any stage, even during COVID times. Overall, there were probably over 100 interns that came through my lab since 2007. They are a great way to actually establishing collaborations with universities. And many of those, of course, fund also employment with us. And that's all I wanted to say about the background. Let's dive into the technology now. And I'd like to begin just with a bit of overall context to ease ourselves into the subject matter with answering the question, what is actually motivating this need for innovative approaches in AI at all? So, and it all boils down to deep learning being so incredibly powerful. So first of all, deep learning can solve problems without having the necessary domain expertise. So you can solve problems that you don't understand yourself fully. They are really popular because they're universally applicable. So you can throw it on a lot of problems. And finally, if you make them big enough and you train them hard enough, then neural networks can outperform existing algorithms and humans. And the famous example here is, of course, the ImageNet classification context. And as a result of this, there are 2 profound consequences. First of all, the number of applications will keep on growing as neural networks are increasingly replacing existing algorithms, and we observe this everywhere. Secondly, DNNs will solve previously unsolved problems. This is really powerful. So the most inspiring example was just from the end of last year, the AlphaFold project by Google's DeepMind, which allowed the prediction of protein construction. And that was actually a grand challenge in computational biology. And humans hadn't solved this for 50 years. And now this was cracked with deep learning. So this is a big deal. So we see, as a result, many new machine learning applications beyond the popular computer vision examples, the natural language processing, and the recommender system that we know quite a bit for a while. So on the horizon, we have now emerging, particularly new applications in communications, and I'll discuss these ones in way more detail on the coming slides. Also medicine, drug discovery, high energy partiphysicals, even EDA. Maybe you heard the Synopsys keynote at Hot Chips. That was really cool stuff, having AI design new chips. Actually, I should also mention our Vivado tool now leverages machine learning for guidance of place and route. So it's happening absolutely everywhere. So what's interesting about these new use cases, though, is that they can have very different latency and throughput requirements to those that you see in I don't want to call it historic, but the more well-known use cases are the more popular ones. So if you look, for example, the state-of-the-art in ImageNet classification with ResNet 50, as reported out by the global MLPerf benchmark. So in last year, the best numbers shown were by NVIDIA's largest GPU, the A100, with 65,000 inferences per second, right? Now, in application contexts such as high energy particle physics or communications, you actually need hundreds of millions of inferences per second. Now, they require very different topologies, needless to say, but still, the use case requirements are fundamentally different. So many new applications are emerging on the horizon, and some of which have very different requirements to the ones that we have seen so far. So let's take a closer look at the communications now. So deep learning is increasingly penetrating the space, We see many emerging use cases from traffic classification, traffic monitoring, prediction, network intrusion detection. We even see attempts to replacing full physical layers in wireless and optical communications. For example, the work from DeepSec is really cool. Overall, the ITU is actually identified and classified. So the ITU is the International Telecommunications Unit, so the standards organization, I should say. They have identified over 30 different use cases in the space. And while it's all still emerging, this is definitely on the coming. So as hinted on the previous slide already, DNNs in communications underlie very high inference requirements. So if you take a look at a 400 gig Ethernet link and you assume a worst case packet size of 64 bytes, this would translate into 600 million inferences per second, right? Which is huge. So at 600, if my circuit runs at 600 megahertz, this would mean I have to do one inference per clock cycle. So that's pretty insane. Even at 5G wireless, right, if you have a throughput of 10 gigabit per second, this would require 15 million inferences per second. So just going back to the example on the previous slide, that's 3 orders of magnitude higher than what was shown in computer vision in 2020. So in addition, the applications are often latency sensitive, not only high throughput, but also latency. So whenever you have your neural network in the form of a cognition cycle where you have feedback, the latency would translate into buffer requirements. And at 400 gigabit per second, that's like drinking from the fire hose. So an upshot here is ML will increasingly penetrate both wireless and wired telecommunications, and the throughput requirements are extremely high, and many applications are latency sensitive. So that's the context here. At the same time, compute and memory requirements are growing in DNNs at an incredible pace. So here shown is the relatively famous chart from OpenAI. X-axis is in years, Y-axis are compute requirements in petaflops on a logarithmic scale. So the compute has doubled since 2012. Every 3.4 months, according to this piece of research. It's visualized with the red line in this chart. Whereas, you know, Moore's law offers doubling every 18 months the performance capability of your device. So that's actually the black line. And that was only the case while Moore's law was still well and kicking. And as you know, that hasn't been the case in recent years either. So it's even worse. So it's probably more like the red line. So you have the compound effect here. So you have to fill that gap from the black and the red arrow. It's a double whammy. So as a result, innovation is needed to make this happen. And let me tell you, there's a lot of innovation going on. And seriously, the space has been really exciting over the last few years. It's been more exciting than the other 25 years that I've worked in the space. And there are a lot of innovative and exciting approaches happening. From one of my favorites is the Cerebras wafer scale computing, right, where you have the chips the size of your dinner plate, 3D die stacking to quantum and analog computing, really exciting stuff. So in this talk, we'll focus on the perhaps less speculative approaches, which leverages specialization in computer architectures to achieve the required performance scalability. And I'll refer to those as deep learning processing units, or DPU for short, but others might call them IPU, or you heard all about GPUs on Wednesday, NPUs or similar. So let's just agree we're going to call all of them DPUs just for the duration of this talk. And there are many startups operating in this space. I am not going to list them all, but there's Habana, Nevada, Sambanova, Graphcore, just to name a few, but also hyperscalers are building their own. So think of Google's TPU from Mike Sutton's keynote. Then there's AWS Inferentia, who was Ascend, and even in the automotive space, Tesla is building its own custom silicon. So I'll zoom into the DPUs now, but before we go in there, let me just say a few words about GPUs as well, because of course GPUs are playing a major role in the acceleration of machine learning workloads. I used to have them actually listed as a separate category, but GPUs are getting increasingly specialized in their hardware for machine learning workloads too. So just think of the tensor cores. So the lines are starting to get really blurred. Okay, so with that out of the way, let's dive into the DPUs now and see where FPGAs actually fit into this picture. So DPUs in general, you can build either with FPGAs or with dedicated silicon approaches. And there are some simple basics at play here that you're probably well familiar with. And I try to visualize this with the charts here in a very simplistic sort of way. So if you look at this chart on the left-hand side, it shows cost on the y-axis over cost to produce a specific volume of devices, whereby the volume is actually on the x-axis. So with dedicated silicon, and I call them ASSPs here, that's the red line, you might think of them also as ASICs, or maybe we could call them unprogrammable devices. That would be more accurate, whatever you want to call them. The point here is that initially we have a very high NRE, but then the volume production gets much cheaper. And for FPGAs, it's the opposite, right? So the NRE is much lower, but then the device cost is higher. So as you increase the volume, the line rises much faster. And then there's, of course, the well-known crossover point. So when you're to the left of this point, it makes sense to stick with FPGAs from a cost point of view. And to the right side, it makes sense to build your ASSP device. And this chart applies to many application domains, including deep learning space. Now, as you start specializing your architecture for DNNs, the potential sales volume will actually decrease, and it becomes hard to amortize the cost for the device. And that's when FPGAs get attractive. For example, nobody would build a ResNet 50 accelerator in ASSP. That would be way too specialized. Now let's look at the performance versus specialization in the second chart here on the right-hand side. So here we have performance on the y-axis and the degree of specialization on the right-hand side. So increasing specialization improves performance. The more I customize the device, the more performance I will get out of it. So that applies to ASSPs, right? Which I have here again in the red line. But at some stage, I'll reach my crossover point, and it doesn't make economic sense for me anymore to specialize the device even further, as it impacts my sales volume. And that's where the big opportunity for FPGA starts, right? Because with FPGAs, I can specialize to the wazoo, right? I can play with programmable interconnect, with programmable precision, with programmable operations, whatever you guys come up with, right? We can specialize so much that we can significantly outperform the ASSPs despite their initial performance benefit. This is of course not universally true, and this is a simplified version, but there are many applications where I think that we can actually produce better fits for the use case with our devices. And I'll show you later one of those. So the opportunity for FPGA lies in the ability to specialize more than everyone else. This leverages the FPGA to its maximum benefit. So let's now take a look at some innovative approaches with FPGAs to AI. And these are just the ones we've been working on in my team. I want to acknowledge that there are many other cool ideas in the community being investigated. So we classify the DPUs by their degree of specialization from left to right here on this chart, whereby the most specialized devices are the furthest to the left and furthest to the right, and the most generic, the furthest to the left. So with the increasing degree of specialization, as you'd expect, we get improved performance and increased efficiency. So we identified 3 categories here, but there are not really hard boundaries in between. In reality, this is more like a fluid spectrum. So on the far left-hand side, we have the first category, which customizes for DNNs in general. The architecture consists typically of a matrix of processing engines, and we refer to it as MPE for short. In the middle category, we call streaming data flow processors. These customize for the specifics of a topology. So here, for example, I would build dedicated ResNet 50 accelerators. And then on the far right-hand side, we have the extreme variant, where the circuit becomes the neural network. So the topologies are fully co-designed for the hardware architecture. So let me discuss these individual categories in more detail, starting with the matrix of processing engines first. So matrix of processing engines, or MP for short, looks something like this. We have a chip with a matrix of processing engines. These can be MAC, so simple multiply accumulate. They can be VLIW processors or vector processor. We have a bit of on-chip memory buffering, we have a DMA, and we have probably some sort of external memory system. And this is, of course, strongly simplified, but I'm trying to get across a point. So we refer to these architectures as a layer-by-layer compute because the way they execute a DNN inference is they first load a batch of input images into the on-chip memory, then they schedule the compute of the first layer onto the processing engines. They execute, buffer the results, then they execute the second layer, buffer the results, and so on and so forth. So batching or processing of multiple inputs in parallel is really important for these devices to achieve compute efficiency. For example, if the first layer had only enough compute for 4 of the engines, and I only process 1 input image, then I would only get 25% of utilization or achieve only a quarter of the peak performance, which is very poor. Whereas if I process 4 input images in parallel, then I would get 100% utilization. So batching is really important to get the throughput on these devices. However, they come at the expense of latency because I first have to collect for input images and buffer them, and then after each layer compute I have to buffer 4 images. So the latency of the overall system is proportional to the batch size, and that's important to understand because that's a key advantage of the data flow architectures as we lose all of that need for buffering and high batch size processing. So these architectures are customized by specializing the processing engines in that they only support the operators, right? So by only operators that are popular in DNN, so mostly multiply accumulates, right? And in the types, they also specialize in the types of ALUs. For example, they have vector and matrix-based ALUs. Think of the tensor cores in the TPU. But they are customized for machine learning in general, and they can execute any workload in principle as long as the operations are supported in the hardware. So in summary, MPAs are really great because they can cater for this broad range of applications with one highly optimized architecture. And this works really well for computer vision and natural language processing. So Vitis AI is the in-house Xilinx example of an MPE on FPGAs. So this architecture is highly optimized. So it does double pump multi-lane DSP implementations. The clock frequency is optimized to the absolute maximum and so on. So it's probably a little bit hard to see. It's a small image, but this actually shows the architecture of what's instantiated inside the FPGA. And all you need to see is that there's basically processing engines which are arranged in 2 directions in essence. On top of this, Vitis AI offers a comprehensive stack of predefined models, everything that you like, brings mainstream framework support, and offers a dev kit, including compiler, quantizer, optimizer, profiler, and runtime. So on to the next category now. So we're getting a good bit more specialized now with the data flow processors, or DF for short. And the tricks that we're using with this approach are a streaming data flow, of course, second, reduced precision, and third, fine granular sparsity. So with data flow, we can specialize now for individual DNNs through customized architectures where we customize not only for the specific operations like the MPE did, but also for the specific connectivity in the given DNN. So the DNN that is shown here on the right-hand side is in essence co-created in the FPGA, and all layers have dedicated compute resources in the device, whereby the compute resources are proportional to the compute requirements in each layer to balance the throughput through this pipeline. So the inputs are then just streamed through the architecture. So back to back, they're going through batch size 1. So this extreme specialization brings advantages over the MPE approach. Firstly, efficiency, because we only instantiate what's needed. Secondly, latency, as we don't need to buffer before and after the layers anymore. We're just streaming everything back to back through. And finally, either lower resources or higher throughput. So let me explain. So with Dataflow architectures, I can scale the resource footprint down to fit into a smaller device by removing compute resources from each layer, or that would look something like this. Or conversely, I can scale it up to run at much higher throughput by adding more and more compute resources proportionally in each of my layers. So this would look something like this. And in the extreme case, if I have enough resources in my device, what I can do is I can fully unroll my DNN in the FPGA, where every operation in my DNN has its dedicated resources. And at this stage, my architecture will run at maximum speed and classify at clock rate. So at 200 megahertz, this will give me 200 million inferences per second. And this is how I can achieve these extreme high throughput requirements in the emerging applications, such as communications. By the way, when we have these fully unfolded or unrolled implementations, we talk about fold one. So the nomenclature is basically fold X refers to a design which is 1x of the throughput of the fully unrolled one. So upshot here is the architecture can scale the performance to meet these new requirements by specializing to a much greater extent than we can with the MPE. So let me show you now an example from Finn, so our project in the space, what such a data flow architecture really looks like. So each layer is constructed from two components. The first one is the matrix vector threshold unit. This handles all of the compute for convolution and fully connected layers. And then the second one is the sliding window generator, which buffers and reorganizes the incoming stream of data such that the MBTU can process it. It's basically, think of it as a really sophisticated object FIFO. The key features of this architecture are, so first of all, the unit has streaming interfaces on input and output, which makes it really easy to construct the full neural network out of layers which consist of these components. And it makes it really easy to integrate it into larger system and support low latency processing. It is highly customizable through the C++ template classes that we use to describe them, and which allows the user to specify the data types both on input and output. So we can have basically any unsigned fixed point integer representations on the input and the output. And finally, we have parameters for defining the degree of parallelism to control the resource footprint and throughput. So we have two parameters for this. The first one is the number of processing engines, which determines how many output channels I can compute in parallel. And the second one is the SIMD width, which determines how many product terms I can compute in parallel. Adjusting the level of parallelism is what allows us to adjust the performance and resource requirements of the overall design that allows us to basically scale it up and down. And as we discussed on an earlier slide already, the folding factor is basically determined by SIMD and PE here. A second form of customization that we exploit with FPGAs is reducing data type precision. It's quite a popular idea, and I'm sure you've come across it already or using it yourself. So the idea is basically to reduce the data types during training of the DNN as much as possible while still meeting the accuracy target in my application. So here are the benefits that I get from this. First of all, it reduces my hardware resources. For example, if I reduce my multiply accumulate from operating at 8-bit to 1-bit, the hardware footprint of this operator shrinks by, roughly speaking, 70x. And when I shrink my compute operator, that means I can instantiate many more of them. And because it's completely parallel, the application, this directly translates into performance scalability. So we've actually micro-benchmarked this for both HLS and RTL. Here you can see the LUT cost over the complexity of your bit products. Second benefit is that it reduces my memory footprint, of course, for the weights in my DNN. Let's consider ResNet 50 with 25 million weights. If I store them at 32-bit, then I need over 100 megabytes. If I just store them at 1 bit, then I need 3 megabytes, which I can easily store on chip and avoid any potential memory bottlenecks. Also worth noting, as every layer has dedicated compute resources, we can completely mix and match position across layer, and with that exploit custom arithmetic at a greater degree than MPEs, right? So I can have different activations and different positions for weights in the same layer, and I can completely mix and match that over all the layers. And this is something that I can't do with an MPE. So finally, it also saves power. So I won't actually elaborate on it here, but it should be intuitively clear. So there are massive benefits that I get from reducing precision, namely performance, resources, power, and memory, everything you care about, which we exploit with Fin. So however, it requires that you need quantization support in your training library. And a third form of customization is pruning. So the idea is basically to leverage pruning of all synaptic connections below a certain rate, as they won't contribute to the output significantly. This, of course, dramatically reduces the compute load. So it should be clear on why that's actually a really good idea. The resulting topology in its most extreme form will have irregular sparsity, as is shown on the top right part here. Irregular sparse topologies result in irregular compute patterns, which are, of course, really difficult to parallelize and therefore hard to accelerate with vector or matrix-based execution units, such as an MPE. So with streaming data flow, as shown in the lower two figures here, we can see each layer and each neuron represented. And when it's fully unrolled, where every neuron and synapse is represented in the hardware through dedicated resources, then we can actually take fully advantage of fine granular sparsity. And what's more so, the hardware synthesis process will actually do it for us. It will automatically remove the relating logic and optimize the overall design whenever there's synaptic connections with the weight zero, which was very nice. So you think this was extreme, but you know what, we can still go further. So we're going now to the far right, the most extreme variant, where my topology is fully co-designed for my hardware architecture. So in essence, here I'm no longer specializing my hardware for the DNN, but it's the other way around. So the circuit becomes the DNN, and we refer to this project as LogicNet. So let me explain this in a little bit more detail too. So the main idea behind LogicNet is that a lookup table in your typical FPGA fabric can be identical to a neuron. So any neuron with 6 binary inputs and a binary output, it can have floating point weights, batch norm, threshold activation, it doesn't matter. This can be mapped one-to-one to a lookup table in our FPGA fabric. And by the way, let me say, there are ways to scale this to more inputs and higher precisions inputs and outputs. But let's keep it simple for now, just so you follow my line of thinking. So with this, we can then turn the whole problem onto its head. So up until now, what we did was we pick a DNN, then we train it. And during the training process, we adjust the parameters of the DNN while iterating on training data set until desired accuracy is achieved. Then we optimize the hardware for it and deploy it. Now with LogicNet, we can do it the other way around. We start with the circuit. So we pick a circuit, right? And assume that that is our unrolled DNN. This DNN, by the way, is naturally sparse to suit the limited fan-in of the lookup table. So ideally, we would have 6 inputs per neuron, and but it can be higher too. And the interconnect in the FPGA, so it suits our fabric particularly well. Then we train this DNN, whereby during the training process, we again adjust the parameters of the neural network until we achieve the desired accuracy. But this time, the parameters directly map onto lookup table contents. And then you can deploy it, whereby the circuit is the maximum performance by the design and will classify at clock rate. So you might wonder at this stage, now hold on a second, how is this different to the fully unrolled data flow architecture? So compared to the fully unrolled data flow, this architecture is optimally suited to your hardware. It caters to the sparsity of the interconnect and the limited fan-in of your lookup tables. And thereby it can achieve even higher performance. You will see in the results section where we can go with this. So in summary, LogicNet will give you maximum performance by design and classification at clock rate. Okay, so just summing up these options that we have there. So there's a unique opportunity for FPGAs because, you know what, we're the masters of specializing hardware. We can leverage reduced precision arithmetic with arbitrary bit widths. We can mix and match precision between layers. We can implement fine granular sparsity, and we can leverage streaming, layer parallel, data flow architectures, and we can even learn circuits. So I'm sure, and I'm even sure there's much more that we can still do and that you guys might come up with. So all I want to say is that this high degree of customization does not work on for the ASSPs anymore. So how much do we actually benefit from these specialized? I mean, it's really cool, all the stuff we can do with FPGAs, but what's actually the measured benefit that we get from this? So let's take a look at an example. And this one here is line rate traffic classification as part of a larger network intrusion detection system, where the intent is to detect packets with malicious intent, such as those sent by hackers, viruses, or malware. So the block diagram looks something like this. We have network interfaces, layer 1 to layer 3 processing on ingress and egress. We have packet processing, feature extraction, which, for example, retrieves important header or flow information that goes into the traffic classification engine itself, which is followed by a packet filter, which will, depending on the output from the traffic classification, either drop or pass the packets, and then it basically goes out over the network. So this type of traffic classification is traditionally implemented by hand-coded rules. So you have a few smart security guys which always observe the latest trends and come up with the latest rules and things that we have to implement into the system. But neural networks are emerging as a really popular alternative. So the goal here is to implement such a system whereby the application requires very high throughput and low latency. So to avoid introducing bottlenecks on the network, the classifier needs to process packets at line rate, which, if you recall from the earlier slides, is for 100 gigabit per second, 150 million inferences per second. The classifier is also latency sensitive, as I need to buffer all incoming traffic while I'm deciding what to do with it, right? So that means every millisecond of traffic translates into tens of megabytes of buffers, right, which is beyond on-chip memory capacity. So that gets tricky. So let me show you now what we can achieve here with the various forms of specialization. So here are the implementations that we considered. All of them are in the same FPGA. It's an UltraScale Plus V09P device. So on the far left, we have the MPE implementation, which was done with Vitis AI. It's a 3-layer multi-layer perceptron, relatively small in size with 92,000 operations, and it uses int8 arithmetic. In the middle, we have 2 data flow processes generated with FIN. One is fully unfolded, so fold factor is 1, and one is fold up 8 times, so it's fold factor 8. This implementation uses the exact same network as the MPE, but the network is quantized down to 2-bit weights and 2-bit activations. So same network, just reduced precision, and the one which is fold 1 will also leverage sparsity. And then to the far right, we have a LogicNet implementation. Here, the network, as described earlier, is fully co-designed with the hardware, and it is smaller. So it's 6x less operations, but it has similar accuracy to the rest of them. Most importantly, it's really sparse. So if you look at the number of inputs per neuron, this one only has 7, which fits much better the fan-in of our lookup tables and the interconnect on the FPGA fabric. So those are the 4 implementations whereby we have an increasing degree of specialization from left to right. So let's take a look at throughput and latency of these implementations. So the MPE implementation, again, shown on the far left, is as expected, the lowest in performance, achieving 22,000 inferences per second with a compute latency of 26 microseconds. By the way, when we measured latency, this was with chip scope, right? This is only around the neural network. So we excluded all data movement overheads from this measurement. So the folded data flow, this is fold 8, clearly shows the speed up that you get through the reduced precision arithmetic, scaling performance by a full 3 orders of magnitude to 25 million inferences per second. Also, we can see a dramatic latency reduction from microseconds to nanoseconds, which is the result of the data flow implementations, right? Where you inherently just remove all the buffering before and in between the layers. So only 240 nanoseconds measured here. So when fully unrolled to fold factor 1, we can scale the performance up to 300 million inferences per second, and we reduce the latency further to 18 nanoseconds. So finally, and by the way, latency again down to data flow, speed up is reduced precision. So finally, the LogicNet implementation on the far right delivers as expected the highest performance. So this gives you 471 million inferences per second. So another factor of 2x that we gained, and it halved the latency as well. So it goes from 18 down to 9 nanoseconds. So you can see the additional benefit from the fully co-designed solution. Remember, the sparse connectivity in LogicNet simplifies the logic in each neuron, which means less pipeline registers are required, which will decrease the latency. And also the sparse connectivity simplifies the routing, which allows us to increase the clock frequency overall. So this design, of course, has a clock frequency of 471 megahertz, whereas this one here is at 300 megahertz. So overall, the example, and it really showcases how the specialization can scale the performance and reduce the latency by orders of magnitude. So that is a fantastic benefit, but which is only possible if your end application is amenable to it. And in this case, it allowed us to meet even the requirements that you would encounter in the communication infrastructure. Remember, we're looking for hundreds of millions of inference per second. So let's take a look now at what is actually the resource cost. I consider here both compute resources as well as memory resources. So we're showcasing in the table and the chart LUTs and DSPs for compute and BRAMs and URAMs for memory. So why does AI is the largest? It actually requires 122,000 LUTs and over 1,000 DSPs. And that's, of course, the int8 arithmetic that you have here, which causes the DSP counts. So fold 8 reduces resource cost despite having the 1000x speed up. So it only uses 44,000 LUTs and no DSPs. So again, the reason is the magic of the reduced precision. Further unrolling should in principle increase the circuit, right? Because I'm making the hardware more parallel. I'm throwing more hardware at the problem. However, depending on your weights, the synthesize optimizes a lot out of the circuit. So all synaptic connections with 0 disappear and memory gets merged into the logic of the neurons. So the result that we've seen anything from 8,000 to 69,000 LUTs. And finally, LogicNet offers the lowest compute cost with 16,000 LUTs due to the limited connectivity inside the DNN. So in summary, customizing arithmetic, sparse implementations, and learned circuits greatly reduce the resources and improve the device's efficiency too, on top of the speed up. So in summary, this example illustrates the trade-offs between specialization and performance and efficiency that can be achieved. And in more detail, custom arithmetic is really effective to scale performance, data flow to reduce the latency. This only works when your application is amenable to the proposed optimization. So to be specific, if you can't take, if we hadn't quantized this neural network down to 2-bit, our results would be very different. But if it is amenable, then you really have the opportunity to meet even the extreme requirements that you face within the communication infrastructure. And there are many more applications there to be explored, by the way. In regards to resources, the reduced precision, fine granular sparsity, and learned circuits been very effective to improve the efficiency. And let me finish this example just by saying that this is a use case which makes most sense with FPGAs. Now, having said all of this, while we only compared FPGA implementations with each other, I'm actually convinced that the same argument will hold true if the MPE were a real process. I mean, 1000x is a massive speed up. So, but more benchmarking to be done for this. Now, the big challenge here is with all of these specialized solutions, how can we actually enable a broad spectrum of end users being able to leverage specialized hardware architectures and co-design solutions? How can we make this technology accessible? And this is essentially the aim of the FPN project. So to provide a fully customizable end-to-end solution stack for highly specialized DNNs and FPGAs. So a basic flow, a typical flow in this solution stack looks like this. The user trains their specialized DNN with various algorithmic optimizations. For this, we have Brevitas, which is a PyTorch library that allows the user to train highly efficient DNNs with reduced compute and memory costs. This is then exported into an ONNX intermediate representation, which is passed into the FPN compiler. This one applies various hardware optimization, generates the dedicated FPGA accelerator, so creates the Dataflow architecture, whereby we leverage code-generated high-level synthesis descriptions for the layers. And finally, the generated accelerator is created as an IP, can be integrated into a system and deployed. So we have deployment flows for various platforms, including Pink, RSoC, and Alveo. So in summary, FPN provides you an end-to-end flow and makes quantization and data flow and fine granular sparsity accessible to a broad spectrum of end user. Also, I want to stress that it was imperative for us to make FPN open source available. So it has been designed for modularity from the ground up, not only because it's essential for transparency and making the solution sufficiently flexible to adapt to this fast-paced field of DNNs, but because we're convinced that it requires a community effort to have impact here. These are complex design. There's an increasing amount of applications, and we're only scratching the surface on the possible design space. So the problem size is well beyond the scope of what we can do in a single research team. So upshot, FPN is made for the community to be used. It's made for you to give you a starting point, and we really hope by working together we can make a big difference here. In regards to status, we see community starting to pick up. So Brevitas, the training library, has been downloaded 60,000 times, the compiler over 10,000 times. We have customer engagements. We have put a lot of effort recently on training material to make FPN easier to use. We've been running tutorials, but also have tutorial videos on YouTube. So check out our Sightings research and open source channel. And finally, we have many new examples like the network intrusion detection. There's a face mask detector from Walter Stecheles' team, and a new example from Saeed at Delft is in the makings. Watch out for that one. And we also started to work on modulation classification with Radio ML with Paderborn and posted this as a challenge as part of the global ITU AI for Good challenge. And there will be hardware examples coming soon. So if you're interested in collaborating, we'd love to hear from you. We also provide free infrastructure for experimentation in form of these academic compute clusters, or XACC for short. There are 4 worldwide, 2 in the US, 1 in Switzerland, and 1 in Singapore. We're working actually on adding a couple more, so stay tuned for this. And what I want to say is they're free to use for you, and they're intended as an enabler for the research community. So they're really different from AWS and Nimbix because they're flexible. You can play with shells. They have network nodes, FPGA node-to-node connectivity. And they allow you to actually collaborate by sharing the same hardware. So to give you an example, the one at ETH Zurich has 5 servers, 10 high-end FPGAs, and all interconnected node-to-node and via switch to a 100 gig Ethernet network. So if you'd like access, let us know. So Gustavo Alonso, who many of you might know, is actually looking after the one at ETH Zurich. It's already seen good adoption with over 100 users, but there, let me assure you, plenty of capacity. We also have a lot of designs available and reproducible on XACC. If you're interested, have a look at that URL on the slide. So for example, in regards to applications, there's of course Fin and Vitis AI, but also BLAST library, DNA sequence alignment, N-body simulation, just to name a few. And in regards to framework and infrastructure IP, I would like to specifically mention that we not only have 100 gig network stack with TCP IP, but also releasing MPI collectives library together with ETH Zurich, Politecnico Milano, and Ken and Lucian and my team. So that's coming shortly. Oh, and with that, we're already reaching the end of my talk. So how time flies when you're doing all the talking. In summary, spectrum of innovative architectures emerging to address compute and memory requirements in DNNs. With specialized FPGA solutions, we can be scaling performance further than anyone else. With the NITS example illustrates, we really should leverage this. Tools such as Fin and HLS4ML, and there are others out there, are needed to make the technology accessible. And there is an increasing amount of emerging applications. There's plenty of space for all of the researchers here where we can have truly great impact. I would really like to encourage you to explore. And I would like to encourage you to use the tools such as Fin and HLS4ML. We have built them for you to give you a starting point. And together we can advance and accelerate innovation collectively in our field. So let me conclude by saying there are not enough FPGA engineers in the world. So we need to leverage this open source and community efforts to make a difference. And with that, thank you so much for attending. I'm more than happy to answer a few questions if you have any. And please reach out if you want to collaborate, use XACC, internships, or whatever else interests you.
Okay, thank you, Michaela. Thank you for this interesting talk. We have some questions from you. The most of them are related to LogicNets. So the first question is if we can make the training on LogicNets in a fully co-design mode. You spoke about FPGA acceleration, but I suppose the question is how we can use LogicNet in a co-design mode.
In the sense, can it be used for other devices, other architectures? And the answer is 100% yes, that principle stands. It's just, it just happens that there's a beautiful fit with the lookup tables. So it might be much more complex to do this, for example, with processing nodes, etc. But there are ways of doing this.
Okay, there is another question about LogicNets. How do they fit in the current Xilinx tool flow?
In the official product portfolio or within the Fin tool flow?
I suppose it is in the official project.
So at the moment, right, we have Vitis AI, right, which is the official Xilinx product, and it's fantastic for what it does, right? So we're working in Xilinx research, right, where we have this whole open source initiative where we're trying to do community research work, and in this space is where LogicNet and Fin sits. And while the intent is that eventually we want to bring LogicNet into Fin, currently it's open source released, so I please go and have a look at it. It has example designs and it has its own tool flow at the moment because, you know, these are the first examples that we made. And of course, we leverage components from Fin as well. Eventually, the plan is to bring them all together, but integrating is always work. So this always takes a little bit more time.
Okay. Actually, there are many questions. Let me pick one more here. The question is related to what is your opinion about the new and more complex technologies like transformers, BERT, etc. And what do you believe if those new modern technologies are quantization friendly? So can we apply quantization new model topologies like transformers?
Yeah. Really great question. So there's every use case. With every data set that comes to it, will be differently sensitive to the different forms of optimizations. Now, for BERT, for example, there's a quantized version was actually described in a research paper probably just about 2-3 months ago. So there's been first people attempting quantization on a transformer topology with success. So there's first indications that this will be possible. There's also been recently a new paper released on quantization of embedding layers, which become popular in particular in the context of natural language processing as well as recommender systems. They seem to be amenable as well. But having said that, we don't really know beforehand, right? Before we have the data set and the topology, whether it's really quantization friendly. And I'm convinced there are always topologies and use cases where quantization is not possible. There was a paper from Facebook which talked about how they have models where they resort back to half precision representations for inference, right? Because they couldn't actually quantize it with sufficient accuracy down to int8.
Thank you. So let's move fast to the next question because you have many questions here. How are the LogicNets different from LogicNet from Imperial College London?
So if I give a really fast and simplistic answer, then LogicNet, it's very similar, just that LogicNet takes it one more step more extreme, whereas for LogicNet, if I recall correctly, there were still the popcons in a separate part. But there's also the NullaNet approach. So they are very much related, trying to do the same thing. LogicNet is perhaps the most extreme here.
One question about we have one more question about the new models like transformers, BERT, etc. Do you have do you know or can you estimate how the performance in those new models compares to the FPGA performance compared to GPUs and TPUs?
I don't have the numbers at the top of my head. So we haven't implemented a transformer network yet with it, but it's on the plans. I mean, these topologies becoming so incredibly popular. So we are definitely keeping an eye on it, and it's in the pipeline. Once we have it in Fin, once we can get it through the training flows or through Gravitas, we have a tool which will give you a resource cost estimation, which directly translates into performance. So once we have it in the training tool, we could actually estimate it, but right now we don't have it in, so I don't have a good answer for you. But actually, this could be a really good subject for collaboration, if I might say so. If somebody wants to work on transformers with Fin, we'd be delighted to work with you.
Okay, there is another question. Do you have a methodology to determine the lowest precision to use that still gives the same results?
Yeah, I love that question. Yeah,
yes, it's a very tricky one. Yes.
Yeah. So actually, Alessandro, who designed and built the Gravitas tool, and my team. So he had a really great idea where he represented the hardware cost of the bit precision in the loss function. So during the training process, as Gravitas it optimizes not only for accuracy, but also for hardware cost at the same time. And thereby, I don't want to say it's the optimal position, but it definitely minimizes the precision in the topologies. And the results were very, very encouraging.
Okay.
There's actually, I think also in Songhan's, I think they've done it with pruning and then expanded to quantization, where they're using reinforcement learning as a methodology to optimize the quantization. But then you have basically another loop around the whole training process, whereas in Brevitas, it's done during the same training run.
So another question is a very interesting one. Can we extend the specialization for DSP and BRAMs similarly to LUTs specialization that you mentioned? Do you have any plans for this?
So I'm not sure to what it refers to, like using DSPs and VRAMs as well. We're using DSPs. We can use DSPs with FIN. It's basically we have HLS description for each of the layers, and you can specifically use them to target DSPs and, for example, start introducing multi-lane DSP implementations. But we haven't done this. Again, excellent subject for for collaboration and future work.
Okay, we need to move to the next session. Yeah. So there are a couple of more questions. Sorry for this, we cannot cover everything here. So Michaela, we would like to thank you for this interesting presentation. Okay, let's move now to the next session.